Hi, I'm actually here today, and today we're going to cover halftoning, but I'm waiting for the computer to finish booting up. I guess, let's see. Let's see. Let's see. So, digital halftoning. Digital halftoning is a very interesting area. Oh gosh, what is this doing? Close tabs. So you can switch over to the computer. But I'm not sure what this means. How do you... Hold on. Okay. Does anybody understand this? Oh, I see. Okay. It's too intelligent for me. Okay. Digital halftoning. Okay, so many rendering technologies only have binary outputs. For example, printers can either fire a dot or not. That kind of rhymes. Halftoning is a method for creating the illusion of continuous tone output on a binary device. Okay, so effective digital halftoning can substantially improve the quality of rendered images at minimal cost. So what is digital halftoning? Well, there's a lot of devices where you may want to display images. Well, first of all, halftoning is an example of sort of a broader class of problems, in which you want to represent continuously valued signals by discretely valued signals. Okay, and sort of binary is a limiting case too, because anything less than 2 is 1, and 1 isn't very interesting. So with 2 levels, you can approximate. It's like 1 bit of quantization. Okay, so digital halftoning is a very important application for that, because there are some practical limitations in real rendering devices. Many classic devices for printing either print a dot or don't. Now, there are alternative technologies that exist for what's called continuous tone printing, which allows you to produce a variation gray levels at each pixel. That, if you have that, then you don't need halftoning. But most widely available printing technology it requires some form of halftoning, even if it's sometimes multi-level. So really, there's kind of an underlying concept here, which is very counterintuitive, which is that if you have a signal, okay, so let me draw something on a pad. Okay, so can we switch over to the pad? Yeah, great. Okay, so if you have a signal, x, okay, and you put x in, so we'll make it a function of time, and you put it into a quantization system, okay, a quantizer. I'll call it Q, okay, and that produces an output y of n, right? It would seem like the most intuitive thing to do. So let's say this quantizer can produce a fixed number of outputs. So let's just take a simple case here that y of n. So y of n here is assumed is a member of the set 0 or 1. Okay, and x of n here is in the interval 0 to 1. Okay. It would seem pretty logical to think that, well, the best thing to do would say, well, q of xm, that's a function. The most logical thing to do is to say, well, I'll put output 1 if xn is greater than or equal to 1/2, and I'll put out 0 if xn is less than 1/2, right? So this would be minimum mean square error. squared error, or MSE, or minimum mean square error, or least square. So you minimize the squared error, or any other absolute error. You're mapping each value to its closest possible output, right? Seems pretty logical to do, okay? But it turns out that in a lot of applications, this is really not the best thing to do. I mean, in this context, it seems so logical. Why wouldn't you always map everything to its closest output? But in fact, you can lose a lot of information when you do that. It often makes more sense, oddly enough. This is one of those great, I mean, there's a few fundamental things in information processing which are unintuitive and surprising, right? And this is one of them. These are good things, really, because they keep us employed. Okay, so what happens is that if you add some noise to the signal, or I'll make it a W for noise, you can actually get a better result. So it's better to add noise sometimes before you quantize. So the reason is that intuitively you retain more information about the gradations of the signal in between the threshold. In the deterministic case, where you just make a hard threshold between the lower and upper value, you lose a lot of information. So it's actually better to add noise to the signal before you quantize. It's a pretty counterintuitive result. So then once you get used to the idea that it's better to add noise, then it turns out that the noise you add, some noise, I mean, the most obvious thing to do is just add kind of white noise or independent IID noise. But then it turns out that that's really not very good. So then it turns out you can there's other distributions of noise that are better. And then it turns out that it's better actually if the noise is actually correlated with the signal. And then so that's sort of what halftoning is about. But the idea is that you want to produce a binary image which is the best representation in some sense of X. And it's for imaging, for halftoning applications, you want this to be the best visual representation of the original image. But more generally, it doesn't have to be visual. It could be some other signal you're trying to quantize, in which case it could be some other metric. But really fundamentally, you retain more information in the signal when you this is called dithering. When you do dithering before quantization, okay? So let's go back to the computer. Okay, so halftoning is sort of an example of a broader class of problems. So just to put things in context a little bit, if you have a threshold, so in general, we're going to have a threshold, and the threshold, well, first of all, the image now is not 1D, it's 2D, so it's indexed by I and J, where I and J are positions in the 2D array, and the values are assumed to go between 0 and 255. So what we're going to do is assume that at each pixel, ij, we'll replace we'll represent the true pixel by a value of either 0 or 255, and we'll do that by applying some threshold t, which is a function of position. Okay, and here we're also assuming that when b is 255, that's you've printed a dot, so dot is black. Okay, so basically the larger x is, the darker it is. So this is the reverse of the way we usually have been talking about images, where we've been displaying them on an emissive display, and a larger value represented a brighter image. So this is the reverse. You can do it either way, but for printing, normally you have absorptance coordinates rather than lightness ones. So larger means darker instead of lighter. Okay. You better, as a practical matter, it's very important to be clear on that when you're talking to someone, so that you don't reverse coordinates. Okay, now, so the obvious thing to do is to just have a constant threshold, and the obvious threshold is to pick t halfway between 127 and 128, and that way every pixel goes to its closest value. it seems like a very intuitive thing to do. It seems, I mean, you minimize mean square error, okay? So this is an example of how the mean square error metric is really poor, because this is the optimal solution from the point of view of the mean square error metric, but it produces a horrible result. Okay, so if you take the image and just threshold it, you lose all the information, because you just get large regions of black pixels and large regions of white pixels, and you don't really have you've lost all the information about the gray level in between, right? So that would be a really bad way of halftoning an image. And no matter how high resolution the printing device is, you'll still get an equally bad result, right? So this is a good example, as I said, of why mean square error is a bad quality metric.
It seems that parts that have kind of pattern or noise, it will be reserved better. So probably this is a good intuition for the case that you mentioned. If we add noise to the
So basically, if you have a lot of variation locally, you retain a little bit of extra information, but somehow this is not satisfying, right? Now the edges are you retain high frequency information along those edges because the high sampling rate spatially. But in the dark or the light regions, you've lost all the information, or most of the information. Okay, so now there's a concept of order dither. So one of the earliest order dither methods, perhaps, well, I'm a little rusty on this, but perhaps the earliest order dither method was, the beer pattern, which we'll talk about in a moment. But basically, in an order dither method, what you do is you turn on the pixels in an area in order. So you take a patch of like an n by n patch, in this case 2 by 2, and then you decide what order you're going to turn those pixels on in. Okay, and if the image is very light, so if the absorptance is 0, then you don't turn on any pixels, and then you turn on this pixel first, and then you turn on that one, this one, and then all 4 of them, right? So now, and you can represent that with a matrix that tells you the order in which you're going to turn them on. This is 0, so it goes first, then 1, then 2, then 3. Okay. Now that leads to a concept of. Okay, hold on for a second. Okay, so I want to actually. Okay, there's actually a concept which I don't think I have a slide over here. So could you come to the pad? Yeah, thanks. So what you do is there's a concept of pattern printing, where you actually take each pixel and you represent each pixel by a pattern. So what you would do is, in fact, I like to tell a story about this. That when I was young, okay, and when I used to go to Atlantic City, okay, on the boardwalk in New Jersey, okay, they used to like have stores where they'd sell T-shirts, and these are the days before they had digital, low-cost digital printers and personal computers. In fact, these are back in the days when if you wanted to use a computer, you had to get card punch systems. You have a physical card and you punch holes in it, and you have a machine that would punch holes in it, and you have the deck of cards would be your program. You put it through the computer, right? So it was pretty medieval. Okay. Well, actually, in medieval times they didn't have computers at all, but okay, relatively speaking. So what would happen is that they still wanted to print T-shirts. They would take your picture on the boardwalk, and they would want to print a T-shirt with your picture on it, right? But they didn't really have any way to do that. So what they did instead is they had impact printers, right? Typewriters. Does everybody remember what people have seen typewriters in museums? Like the typewriters had a little thing on the key, and then when you press the thing, it would go thump and whap the paper, okay, and there was like a ribbon in between there. Okay, so that was called impact printing. So IBM had a major innovation in this domain. It had the IBM Selectric, okay, where they had a ball which had all the different fonts on it, and the ball would spin around to the correct position and wham against the paper. So that was kind of the thing. And then they had another daisy wheel thing they had. So the daisy wheel, I'll draw that on the paper. The daisy wheel had all the letters on individual little things coming out of here. So it looked like a daisy. So that's why it was called the daisy wheel. And the daisy wheel would spin around to the correct location. Of course, it completed all the way around. And spinning around to the correct location, and then a solenoid would fire a hammer that would impact the thing. So you had a fixed set of things you could print, okay? So now at each location, now I'm drawing a little box, but you wouldn't actually see the box. On each location on the piece of paper, you could print a letter, right? Or you could actually print multiple letters. So if you print the letter dot, period, right? That's quite, you hardly fill up any space, right? Now if you printed the letter, say, I, that fills up a little more space. Or if you had L, okay? Now if you printed M and you printed W in the same location, you're starting to fill up most of the space, right? So as you print more and more letters here, you get a darker pattern, right? But you can only print a fixed number of predefined patterns at every location, right? So what you would do is they would print these things, and they would actually draw your face on the T-shirt. But it was the most god-awful picture you could imagine, because you have these huge fonts, and that's 1 pixel, and it's pretty rough, and you can control the gray level. But what you could do, you could perform anti-aliasing. If you saw the person walking down the boardwalk and you said, what are they wearing on their T-shirt? Okay, what you could do is when you look at them, you'd squint. Okay, and when you squint, why would that work? The theoretical reason for that is what?
It's like a low pass.
It's a low pass filter, so it would perform anti-aliasing, right? So it would get rid of, this is a sampled signal with these patterns. You get rid of, filter out all the high frequencies, and when you squint it, you'd say, oh, yeah, that's what they look like, okay? But it was really, really bad, okay? That is called pattern printing. That is the worst possible kind of halftoning, really. Maybe somebody can come up with something worse, but I'm going to declare it the worst right now, okay? So, because you basically have to take a whole set of pixels and replace them. So what happens, if you go back to this ordered dither concept, if you go back to the computer, that you could take this 2 by 2 or n by n array. So how big does n have to be? If you wanted to have, say you want to have 256 levels, right? So 256 is, let's see, 8 squared is 64, right? Oh, hold on for a second. Hold on. 8 squared is 64, correct? So 12 squared is what? 144. 13 squared is, what is 13? What is it?
169.
169. Oh, so we're still not there. 14 squared is what?
96.
So 14 squared should do it, I'm thinking. What is it?
196.
Oh, still not there. Okay, 15 squared. Okay, that's more than 256, right? Okay, so you'd need an array which was 15 by 15. Well, if you're going to do that, you may as well just go to 16 by 16, right? So you take 16 by 16 pixels, right? And then you could turn on the pixels one at a time, and you could get, what's 16 squared? 1024? Huh? Oh, well, hold on, that's correct. Why didn't I just go there right from the very beginning? Okay. I was just taking a little extra time. That was a test to see if you really knew the correct answer. Okay, so if you have 16 by 16, here, could we switch to the pad again?
Over there.
Okay, so that's, let's see, that's 8. Oh, that's 1, 2, 3, 4, 5, 6, 7, 8. So, twice as many as that, okay? I don't feel like drawing it. That's 4. Okay, so this is going to be, this is 8 by 8. But imagine this is 16 by 16. You turn on one dot at a time, right? You get 256 levels. Actually, you get 257 levels. Because you start off with 0, and then so you get one more, okay? So you get 257 levels out of here, right? But now what happens is that if you have an image, let's say you start off with the image that's, I don't know, let's say it's 256 by 2, let's say it's 512 by 512 resolution, okay? There was a time when that would seem like high resolution, but those days are gone. Okay, so that's a quarter megapixel, okay? So you divide 512 by 16 and you get what? 32, is that correct? So you'll only have 32 by 32 of these patterns. Effectively, the resolution will only be 32 by 32. That's really low resolution, okay? That's why you have to squint on the boardwalk, okay? So basically, the resolution is, for pattern printing, the resolution, so the output res, right, is going to be equal to the input res divided by the square root of n, right, in each direction. The number of pixels is going to be divided by n. So that's pretty bad, because you're giving up an enormous amount of resolution. So the trade-off that people make is they say, well, maybe I don't need 256 levels or 257 levels. So they might go down to 128 or 32, but then you're giving up a lot of gray levels. So this causes, so this means there's a trade-off. The trade-off is between resolution and gray levels. You can have a lot of resolution with with one gray level, right? Or you can have a lot of gray levels, but you lose a lot of resolution. So it's an undesirable trade-off. But for a long time, people just assumed that was kind of the way it is. You know, they just, I don't know if they had a proof, or maybe there were a lot of people realized that, some people realized, but it was commonly thought that there was this kind of basic trade-off, and that was just kind of how it was, okay? But then people started thinking about it a little more deeply, okay? So coming back to the computer, so now you have this n by n array here, 2 by 2, so you could replace each of these with a pattern. Well, one thing you could do that would be a little bit more favorable than just replacing each pixel with a pattern. If to replace each pixel with a pattern, you have to take each n by n array of pixels, right? And you have to average them, basically form a single pixel, and then based on that average, then you replace it with a single pattern, right? So, okay. What you can do, though, is you can do the thresholding for these pixels individually. So what you can do is say, okay, what I'm going to do is I'm going to form a threshold matrix by taking this ordered, this pixel ordering. I remember the pixel ordering. I add 0.5, divide by the square root of n squared, and take and multiply by 255, and I get a threshold matrix, right? And now if I take that threshold matrix, and if I take a constant gray level, and I compare the constant gray level to t, then at any constant gray level, I'll get out that pattern that I originally programmed in. But it's a little more favorable, because at least if I replace the constant gray level with the actual pixels, then at least I have the ability to maybe do something a little different at a pixel that's very different than its neighbors. So in other words, if I replaced each block of the image with a single value, I would get out pattern printing. But here, because I'm using each pixel independently and comparing against the corresponding threshold, I get a sort of more information out in my binary image. Now, you might say, well, what do I do if the image is larger than the threshold array? Well, I just repeat the threshold array periodically. And that's referred to as tiling. Because if you've ever been in a kitchen, okay, on the floor, on the floor, typically what they'll do is they'll have tiles, okay? So you have a tile like this, right? And then you repeat the tile, right? Now, the thing about the tiling is that if you're going to have a pattern in the tile, the pattern has to be designed so it repeats, okay? So if you're going to have a pattern like this guy here has to have, like, say, a pattern like that, right? then in order for it to not be discontinuous, you have to have the corresponding pattern here, which means that you have to have the corresponding pattern there, right? So when you design the tile, you really want to think of it being designed like this. So this is a single tile, right? And whatever pattern you have here, you want to make sure that it repeats here. Now, this isn't the threshold array you'd want to use, but whatever you want to use, you want to make, it's like the, I think I talked about it before, where the Space Invaders, or no, Space, what is it called?
Asteroids.
Asteroids, there you go. Asteroids. Then when you go off the edge, you come back on the other side, okay? So this is a torus. Torus. Is that how you spell torus? T-A... Taurus? Is that how it's spelled? I don't know. Well, no one here is disagreeing with me. That's just an indication that there's a lot of engineers in the room, okay? Okay. Anyway, all right? Good. So, fine. So this is sometimes called wraparound. Wraparound, okay? Now, and what it really means is that you want to kind of use modulo arithmetic. Now, what mathematically, the way you represent this is you say that sort of the extended threshold array is equal to T of I mod n j mod n. So for this reason, we usually think about the indices of the threshold array going from 0 to n minus 1, because it makes the mod arithmetic more logical, from formally speaking. Okay? So coming back to the slides, this is the threshold. This is the equation you want to apply. And if you then now the question is, how do you design this threshold mask? You want it to be, like I said, you want it to have this wraparound property, like a tile on a floor in a kitchen. So one thing you could do is what's called a clustered dot screen. And a clustered dot screen, the idea is that, now the word dot, I have to say, is, you might say, overloaded in the context of halftoning. It's used to mean lots of different kinds of things, okay? So we could perhaps call these individual pixels, these individual points that get put down, printed or not, as microdots. And then the whole periodic affair you can call a macrodot. But basically, in cluster dot screening, you take this n by n array and you design it so that as the dots turn on, as the microdots turn on, they turn on next to each other. So you kind of grow a dot out from a single centralized location. And the idea is that, well, there's safety in numbers, and the little microdots want to be near each other, okay? Because if they're all by themselves, they get kind of lonely, and it's not happy out there, okay? Now, what really happens is that in real printing technologies, sometimes the microdots don't like to be that far apart, okay? So it might be various reasons. In electrophotographic printing, what you might call Xeroxing, okay? But we wouldn't actually use that word in this classroom, right? In electrophotographic printing, okay, what happens is that you actually charge particles that go to the paper. So the charged particles, so I forget which way it works. I'm sure, So let's say that the toner particle is the particle that it's basically what you might think of as ink, okay? It's usually like a polymer that when heated it melts, okay? But there's a toner particle is charged negatively, I don't know which it is, or positively, okay? No one here is correcting me, so I'm going to pretend I'm correct, okay? So let's say it's negative, okay? And the paper is then positive, so that the particle of the charged toner particle is attracted to the positive paper, but they're repelled from each other. See, because the like charge on the toner particles tends to repel each other. So let me just draw this a little bit. So you have a sheet of paper, and let's say, and now I'm really going to make it clear if I'm wrong, but unfortunately, okay. So let's say that this is plus, okay, for lack of, I should have looked it up. So this is plus, this is minus, okay, and then there's toner. So the toner is charged up somehow or another. Okay, and what happens is then there's some mechanism for depositing the toner on the page. So the individual particles are of toner are minus. So minus. So this is plus, plus, say, plus, plus. It might be the reverse of this, honestly. I should have looked it up, but okay. So they get attracted to the paper, but they're repelled from each other. So for that reason, that if you try to put just one piece of toner down, it tends to be unstable. That they like to glom together. Okay. Now, the other technology that's commonly used for printing, there's a lot of technologies for printing, but another commonly used technology is inkjet, where they squirt out a little bit of ink, right? So in general, it's easier to squirt out a little bit more ink than a really small amount of ink. It gets tricky, okay, as the quantities get very small, okay? So now, getting back to the clustered dots. So there's a lot of reasons why you might want to actually have these microdots form near each other to form a more stable dot. So what happens is, as the gray level in the as the image becomes darker, then more of these dots turn on in order. So you get a clustering effect. So this is what happens if you use a clustered dot screen of size 8 by 8. So what happens now is that it's almost as if the resolution of the image has been reduced by a factor of 8, but not quite, because there is some detail that's retained because of the fact that the thresholding is local. So for instance, so this is 256 by 256 times 1.5 is the resolution in the underlying image. So you divide that by 8. So 256 divided by 8 is what? So the 8 squared is 64. So this must be 8 times 4, 16, 32. So there's basically 32 pixels across this way, and then there's 32 plus 16 this way, which is 48. Yeah, 48 by 32, okay? But you do retain some more information. Like, for instance, in these higher resolution areas, or at least a longer chin here in this image, you can see that there's a pretty sharp boundary there that's retained because it's a very high contrast. So even though the thresholds are locally changing, there's enough change in the pixel values to maintain that threshold, that edge. Okay. So this is better than that, right? But it still has problems. So you'd say, well, now you have you have some choices. An 8 by 8 clustered dot screen only allows basically nominally 64 different gray levels. So you don't have as many gray levels as perhaps you'd want, because a typical image is quantized to 256 gray levels, right? So you can make that screen larger. So here's 16 by 16, but if you make the screen larger, then you effectively lose resolution. Although, again, you should be able to retain some information on the edges here. But you've lost a lot of information. If you squint, you can sort of see her face. Okay, but so now you definitely have a trade-off between resolution and gray levels. And over here, you can see that the 16 by 16 clustered dot, you can see how it grows. So this is basically just a representation of that threshold array as an image. And this is here you have fewer gray levels. Okay, now so properties of clustered dot screens. It requires a trade-off between the number of gray levels and the resolution, which isn't in general desirable. Relatively visible texture, because you're using a large macro dot, okay, and relatively poor detail rendition. But one thing is that you get uniform texture across the entire grayscale. So, which we'll see later isn't always the case with all half-toning methods. and it's robust to a lot of non-idealities in devices. So it's non-additive spot overlap or spot-to-spot variability or noise. So actually, cluster dot screens are used very commonly in a lot of high volume printing, and in fact they're an analog to this is a digital screening technology, but they're an analog to what was done historically using analog printing technologies. So it's kind of interesting. Let me just draw this again. So what happens is that in the old days, before they had digital printers and they printed, right, often what they would use is they would use high contrast media. So this might be a piece of photographic paper that had the property that it was maybe designed for printing text. So it had the property that so let's say this was the input brightness. It would have the property that if it was absorption, say, I don't know what the scale is here, it would have like a curve that looked like this. So it would give you a high contrast threshold. So below some level, it would be, the output would be, so this is absorption, let's say. So below some level, if it was dark, it would remain dark. And then above that, it would suddenly turn white. And that was good for printing things like text, because you get sharp edges in the text, right? But now the problem is, if you went to try to print some continuous tone object, then this wasn't so good because you'd get a hard threshold. So what they would do is they would actually physically take a photo. So let's say you wanted to copy a photograph on a photocopier that was designed for reproducing text. So when you put the photo on the photocopier and you copied it, you get like a threshold version. So what they'd actually do is they have things, and you can still buy them. They're called screens, okay? And they literally took the photograph and they put it. So this is the photograph, okay? And they literally put the screen underneath it. And the screen had holes in it. It was like a bunch of, they called them like line screens. And they actually had physical black lines on the screen. Before that, they actually used, like a long time ago, things that were effectively similar to fabrics, okay? So if you look at it, there were places that blocked the light, right? So let's just look at one hole and how it behaved. So the light would come through here, and you'd get some sort of distribution of light that looked like this from that little hole in the screen. And of course, this, depending upon whether the region was bright or dark, this distribution of light would be larger or smaller. But because of the high contrast effect of the development on this medium, when it developed, the image that developed would either be a small dot or it would be a large dot, depending upon how large this amplitude was. So essentially, the dot would cause a little blob, right? And then the threshold, the threshold would stay still, but what would really happen is that this amplitude would go up and down, and the dot would modulate its size. So the cluster dot screening is the digital analog. It's using digital equipment to reproduce the same physical effect as what was done in traditional screening, physical screening in real, like, photographic applications. Okay? So coming back to the computer, yeah, so that kind of gives you a sense. A lot of printing is still done with cluster dot screens because it's very robust. Particularly, like, things like, technology keeps changing, but a lot of, like, for instance, printed news material will be done with cluster dot screen. But it's changing because there are some more advanced technologies that people use these days. But it's really quite recent. So, okay, now, people then got the clever idea, why, if you didn't have to keep all the little microdots close together, could you do better? And the answer is yeah. Okay, so what you could do is try to disperse out the index. So instead of turning the dots on, like, all together and keeping them all together, sort of keep them as far apart as possible. And one idea that came up is the so-called bare screen, and it was just a clever idea, which is essentially kind of a fractal pattern. And the idea is you try to get the dots as far apart as you can. So you do that with a recursive scheme. It's pretty intuitive, really. And so you start off with the 2x2 array where you first turn on this 0, 1, 2, 3, right? I mean, you don't have a whole lot of choices. You put on, let's say you put, without loss of generality, you start with this pixel, right? Now it's like, well, you don't want to pick one of the two pixels that's as close as possible, so you took the farthest one, right, to turn on. Now you can either pick this one or this one. It really doesn't matter. It's symmetric. So whichever one you pick, then the fourth one is here, right? So it's fairly logical. And then what you do is you say, well, okay, now I'm going to repeat that process by taking each of these and scaling them a little bit by adding, well, I'll scale them up because now I want to take a 2x2 array and make an array for a 4x4. So the number of gray levels has to increase by 4. So I'll have to multiply each of these indices by 4. But then I'll add an offset to determine which order they go on in, right? And this is the recursion. I think you implemented this in your lab, right? So if you just look at what you actually get, this is what you actually get. So here is you first turn on that pixel, then you turn on this pixel, right? Then you turn on this pixel, and then you turn on where's 3? This pixel, right? Then next where's 4? Here, right? So you they're all dispersed about. Now, it seems like a great idea, and you can prove that it has various optimality properties. Unfortunately, it doesn't work quite as well as you might have hoped, okay? But if you apply it, so you initially look at it and you go, wow, this is like fantastic, because what we were getting before was really bad, okay? Okay, so going back to the comparison, because it seems better than that, right? And hold on, it seems better than that, right? It seems better than that, okay? But, it's like you first have that initial blush of excitement, and then it starts really bugging you after a while, because you look at it, and it's got these strange repeating patterns that occur, and they're kind of annoying. And actually, when you print this, if the resolution of the device is very high, what will happen is that you might get some kind of nonlinear resonance between these particular patterns and the behavior of the device. So what will happen is even when you can no longer see the individual dots, these different patterns will shift the gray levels. So you'll get sort of strange contouring artifacts that will sort of occur reproducibly in different regions of the image. It'll cause it'll cause gray level shifts that also cause like contours in the image. So these textures really have some undesirable side effect. You really like to. What's really bad is that you've got fixed textures that appear in different regions of the image based upon the gray level. But nonetheless, at least from an information theoretic point of view, you're retaining a lot more information here. I mean, you can see all kinds of detail. The resolution's high, and clearly there seems to be an ability to bypass what was thought to be this fundamental trade-off between resolution and number of gray levels, right? So here, now one thing that's interesting, you say, okay, well this is 8 by 8, so 8 by 8 gives me 64 different gray levels. What if I want 256 gray levels? Well, I go to 16 by 16, except for it doesn't really look much different. It's almost the same thing. And that's sort of a property of the Bayer pattern. Because it has this fractal structure, when I build up the larger screens, I'm only shifting by one level. So there's really hardly any difference. But in theory, at least, this maintains a little more information about fine gray levels in the original image. This is the Bayer pattern. Here's a smaller 8 by 8 Bayer pattern. But you can see it's almost like a checkerboard kind of a pattern. Okay, now, then there was a breakthrough that occurred in the industry. So this is kind of interesting. This is like in the late 80s, okay, that people had, at that point, the history of printing, of which I'm not really an authority, but I can give you some anecdotal information that at least has some truth in it, I believe. More of it's true than you would believe, actually. But anyway, okay, so what happened was that printing evolved along with raster displays in computers, because originally computers had like punch card inputs, and they had, it was pretty advanced when they had these high-speed line printers, they called them, where they print an entire line at a time. So what would happen is you'd put in college, you'd have to do computer assignments. So you'd punch all these cards up. You'd have hundreds of cards, and you'd be holding them. And then as you were walking to go put them in, you drop them on the floor, and they got all out of order. And then you'd get really upset. And then you go back and you'd repunch them again, okay? And then you go back and you'd put them in, and then you'd wait in line in front of a window usually with about 20 other undergraduates who were desperate for their output. And you'd stare, sort of like a kid in a candy shop looking through the window with your face up against the glass, waiting for this thing to come out. It would take like 45 minutes for your output to come. So you were multiplying three numbers together, but you'd wait for 45 minutes, and then you'd see this printer would just spit paper out, and then someone over there, the operator, would rip the jobs apart because they had perforated paper, and each person, and they'd put them in a bin, right? So you'd wait for Bouman, or if your name was different, you could wait for a different name. But they'd put it in a bin until finally you got Bouman, okay? And you go, oh my God, and you'd open it up, it would say core dump, right? And then you start all over again. Okay. Now now that was great. So what happened then is people got the bright idea, well, we could have like printers that people could get individual output for themselves, not have to wait in line with 100 other people to share the output from one printer, right? And it could even be like the line printers were like typewriters. They could print individual symbols in fixed locations, so only ASCII text. They said, well, we could also print like general text, or maybe even diagrams, or vectors, maybe drawings, okay? And they could have fonts. Maybe each font could be different. So if you're going to do that, instead of actually having a hardwired typewriter, you have to actually be able to print individual dots. But the idea was mostly you were only going to be printing text, okay? So people then two major kind of breakthroughs were that there was a thing called actually a Versatech, which was an early device, that did electrophotographic printing, but like a photocopier does, or a Xerox machine, okay? Electrophotographic printing, but instead they used the laser to write on the paper, okay? Now this was a great breakthrough that was developed at Xerox PARC, actually. Gary Starkweather was the guy who really did that. And he had this idea of having this octagonal mirror that would spin around and scan the laser across the page. And in each position, you either fire the laser or not, and you could draw. So that would allow you to draw arbitrary shapes of fonts. So now you could print anything you wanted in any font you wanted. Well, this was a huge breakthrough, okay? People could pick, all kinds of crazy fonts, Helvetica and Times and all these other crazy fonts, okay? And, so that's fine. So that was great. So now they had printers. So HP was one of the early people in the Boise area. They commercialized this technology and produced one of the first really popular laser printers, they called them then, electrophotographic printers, that was sort of widely available, for small business use. Okay, it was something that didn't cost, $50,000. It cost something like $3,000, which was incredibly cheap. Okay, so this allowed people to enter the market. But now for home use, that still wasn't very practical to spend $3,000, especially in those days when $3,000 was more like $10,000. Okay, so then what happened is they had this concept of inkjet printers, where they would, as the inkjet head was going across, it would drop individual drops of ink, okay, on the page. Okay, now and people could then buy these inkjet printers for $500, something like that, and they could bring it home and they could print in their own home. They could print anything they wanted. Like they could have any text. They could write a document. They could print it out in black and white, of course. And this was a wonderful breakthrough. Okay, but you couldn't print an image. Okay, you really could only print text. So now the huge breakthrough was, how do you use this device to print an image as opposed to just printing text? There's where the concept of halftoning came in, and that was where the huge sort of technological breakthrough was the idea of this dispersed dot screening, which allowed you to print with your cheap inkjet printer at home photographs that actually looked like the people you took the picture of. So that was an enormous enabling technology that started a multi-billion-dollar industry. Okay? So if you ever think signal processing has no impact, you're wrong. Okay. All right, bye.